Dear students, let's continue our discussion of the calculus of variation in the online mode. So as I told you, the general mathematical framework for the development of this particular technique of the calculus of variation all began with a historical problem known as the Brachistochrone problem, which was posed by Johann Bernoulli in the year 1696. And the problem was posed by Bernoulli as a challenge to the then mathematicians, even though Bernoulli himself knew the solution to the problem. And the history says that a number of solutions were received by Johann Bernoulli, including one by his own younger brother Jacob Bernoulli, Leibniz, and one by Isaac Newton himself. Newton's solution was published anonymously by the Royal Society, but Johann Bernoulli immediately recognized that it was Newton's. And that's an interesting thing. And there's a famous quotation by Johann Bernoulli identifying Newton's solutions. He said, "We know the lion by his clue." ഒരു സിംഹത്തെ തിരിച്ചറിയാൻ അതിൻ്റെ പാദങ്ങളുടെ പാട് മതിയാവും. Exactly, the solution given by Newton was accepted and was agreed upon by Johann Bernoulli, even though he had found out his own solution to the problem. Anyway, the Brachistochrone problem is one of the celebrated problems in the history of physics, which stimulated the branch of mathematical technique called the calculus of variation. So we will focus on the technique of calculus of variation, and we will see how the technique of calculus of variation can be used to obtain the so-called Lagrange's equation of motion in classical mechanics. Moreover, we will familiarize ourselves with some of the common applications of calculus of variation so that we can understand many of the variational principles in physics in its essence. The variational principles in physics are based on the mathematical technique of calculus of variations, and thereby this technique assumes special relevance. And we are familiar by the time with a number of variational principles in physics, which includes one in optics, which is quite famous, which is nothing but the Fermat's principle of shortest time in optics, or we can say in general electrodynamics. And you are going to see a very important principle in classical mechanics in the very next module itself, known as the Hamilton's principle, which is also known as an extremization principle, or it's the principle of least action or stationary action. So there are several principles in physics which comes under the category of variational principles. So all these principles are having sound basis on the mathematical technique of calculus of variation. So we will just discuss this technique in short and try to understand how this technique forms the foundation of many other branches of physics. So as I told you in the introductory offline section, the variational problems in physics are meant to find the maxima and minima of certain quantities. So those quantities are usually known as or represented by functionals. So what is meant by a functional? We are all familiar with the word function. So what is a functional? Mathematically speaking, a functional is simply defined as function of a function. So what's the meaning? For example, if you take y is equal to a function of x, so let's represent it as y of x. So it's a function of x. Okay. Now, if I define another function, if I am defining another function, say capital F, which is a function of y, and you know this y is already a function of x. So the function which I have defined here as f of y, where y is another function, is usually known as a functional. So f is known as a functional and y is actually a function. So functional in mathematics means function of a function. A function, as we know, relates or maps a real number to another real number, whereas a functional connects or maps or relates a function to a real number. I repeat, a function relates a real number to a real number, whereas a functional relates a function to a real number. So these are some mathematical definitions and all. But thing is that we'll see how the variational problems are addressed to find out the maxima and minima of functionals. So to start with, so let's consider the concept of variation first. Okay, in order to consider the concept, understand the concept of variations, so let me consider a particle moving from point 1 to point 2, some arbitrary points whose coordinates are represented as x1 y1 and x2 y2. So you know that there are several paths that can be taken up by the particle in going from 1 to 2, but we are choosing or we are representing two paths which connects 1 to 2, along which the particle may move. So one is a straight line path which connects 1 to 2, and another path I have chosen which is known as a comparison path. So the first straight line path, of course you know, that is the path which connects 1 and 2 having the shortest distance. Okay, in say kinematics or in mechanics, we usually call this distance or the length of this path as what is known as displacement. Okay, so we know from our experience that this straight line path is the extremum path. So as I told you, the word extremum used in mathematics or calculus of variation can either mean maxima or mean minima. Okay, so the reason is that in certain cases we are interested in finding out the maxima of a function or functional, but in certain other cases we are interested in finding out the minima of functionals. Okay, you are already familiar, like for example when you study thermodynamics, even though I'm taking the case examples of functions, in thermodynamics you know that every system prefers to minimize its energy. Every system prefer to minimize its energy, but you know that thermodynamically speaking, every system tends to maximize its entropy. So there are two directions for certain quantities. Either the quantity tends to be maximized, or the system has got a tendency to get some quantity as minimized. So in order to include both these conditions in the variational problem, we are using the word extremum. So extremum can either mean maxima or minima. Okay, so or another equivalent word is what is known as stationary. So a function or function becomes stationary. So you come back to the figure what I am discussing. So you can see that there are two paths. One is the extremum path, which is the shortest path here, or the minimum distance path. So it is the shortest path here, and the other path out of a large number of possible paths, I have taken a specific path which is known as the comparison path. And why it's known as a comparison path? We are going to compare the length of this path with that of the extremum path. Okay, and we will be finally successful in establishing the fact that the straight line path will be the optimum path, or I can say the extremum path. Okay, so that is there. So let's say let's make some constructions more here. So I'm considering some arbitrary point x on the x-axis. So corresponding to a point x on the x-axis. So if I drop a perpendicular there, you can see that it is intersecting a point on the extremum path, and let's denote that point by y, a function of x, and I'm putting 0 for the time being. Okay, so we will see what is this 0 denoting later. Okay, some parameter has got a value 0 for the extremum path. That's the meaning. Okay, now corresponding to the same x, okay, the point on the y-axis is represented by y for a given x, comma, for the parameter alpha. So there is some parameter alpha here, or some scaling factor alpha is here. Okay, so let yx alpha be the y coordinate of the comparison path, any arbitrary comparison path. Okay, so when the value of alpha is different, okay, you will be getting another comparison path. That is the thing. Okay, when the value of alpha, so from comparison of this 2 points, you can understand that in yx0 actually the alpha is 0. Okay, some parameter, some scaling factor alpha has been set equal to 0 for the extremum path, and non-zero for the comparison path. Okay, so that is the point to be noted. Alpha, which is a scale factor, has been set equal to 0 for extremum path. It is set equal to 0 for extremum path, and alpha is set non-zero for infinite possible comparison path, for comparison paths. Okay, we have chosen only one. There can be many. Okay, comparison paths. So let me say. So extremum path is unique path. Okay, so that is the thing. So these are the things. Now you can look at the diagram. So corresponding to the same x, I'm taking the difference in the y between 2 points, one point on the extremum path and another point on the comparison path. So the difference between a point on the extremum path and point on any of the comparison path for the same value of x is represented by delta y in the diagram, and this delta y is known as variation in y. So delta y is known as, see, we are using the symbol delta here, not dy, it's delta y. So delta y for as variation in y. So that is the word that we are using. So actually see, when you write dy, is not, so dy corresponds to some dx. Okay, it is not for the same x. So corresponding to a dy, there will be a dx. Okay, so it's never for the same x that we measure dy. That's why there is dy we are using. Okay, but here delta means delta y, or variation in y, is measured for the same x. Okay, so that's how the delta variation is different from the d variation. D variation corresponds to some finite change in x variation. Okay, whereas the delta variation in y corresponds to no variation in x. It corresponds to two different possibilities. Okay, that a system can take for the same value of x, or one parameter fixed. So that is the thing. So that is delta y, right? So you know that out of these the straight line path is the shortest. So let me go to the next page. So yeah, so out of these the straight line path is the shortest, or the extremum path. So we can represent the straight line path, the extremum path. So the extremum path can be represented as, since it is a as we know that mathematically it is y is equal to something like mx plus c. Okay, y equal to some mx plus c, or in general we can write that y is a function of x, right? So this is the function that we are talking. Y is a function of x. Okay, so where x is the independent variable, okay, x is the independent variable. So be careful about all these assumptions that will be relevant later in our discussion of the equation independent variable. So x is the independent variable, right? Now what we are interested is in the shortest path or extremum path, right? This is the equation of the path. So the length of the path, we are interested in the length of the path, right? Okay, the length of the path, okay, means straight line path here, what we are doing, okay, length of the path connecting 1 to 2, from 1 to 2. So I'm considering the extremum path first. Okay, so how do we find out the length of the path? So from the diagram we can take that I have taken a very small or infinitesimal length ds. Okay, please do not compare its magnitude, it is not to scale. So ds, let ds be a very small okay, section, okay, or infinitesimal distance on the extremum path, and corresponding to some dx and dy. So here you can see what we are using dx and dy, because the dy here is measured for two different values of x whose difference is dx. So that is d variation, and the other one is delta variation. You consider delta variation. You can see for the delta variation it is corresponding to the same x but for two different paths, two different possible paths, one extremum path and another comparison path. So that's how delta variation is different from the d variation. D variation is taken for the same path, okay, whereas delta variation defined for the two different paths corresponding to a particular x value. So let dx and dy be okay, the two sides of the right angle triangle whose hypotenuse forms the ds value. So I can write the length of the path. I am representing the length of the path okay, as some letter j. So it's an arbitrary letter, you can use any other letter as well. So j equal to how do you get the total length of the path from 1 to 2? Can't you just depend upon the technique of integration? So if you divide this okay path into large number of ds, is not ds like this, and you add up all those ds, you will be getting the total length of the path from 1 to 2, which is represented by capital J. So you know, in in this case the best mathematical technique is to make ds infinitesimally small and go for the technique of integration. That is the mathematical technique of integration. So I can write mathematically the length of the path from 1 to 2 along the extremum path. So let's say that that's equal to not only along the extremum path, along any path we can take it, okay, because we are depending on integration. So I can write this is equal to the integral of ds, the integral of ds, where ds is shown in the diagram. Okay, so which I can express in terms of the variables, okay, x and y. So I can write this one as something like root of dx square plus dy square. Okay, so by simple Pythagoras theorem, it can be written as dx square plus dy square, which I can rewrite once again as is equal to root of something like, so if you rearrange it, 1 plus some y dot square dx, 1 plus y dot square dx, where you can understand what is y dot. Y dot is the first derivative of y with respect to x. Because y is a function of x, so y dot is equal to dy by dx as per the notations. Okay, so you will get this equation by just simply is not okay dividing by dx square both the terms, and to compensate it you multiply by dx outside the square root. Okay, so that is the equation. So let me so now you are able to understand. So in the previous equation I didn't write exactly what is the yeah, sorry, I must put some integral simple here, right? Because that is integral is there. I have substitute for ds. So here is there is integral. Now this equation says that you can just now decide that the variables are from okay x1 to x2, because we are performing integration with respect to x here. So I'm writing this one as something like integral x1 to x2, integral x1 to x2, and this quantity I'm writing it as f of, I'm representing this as a function, okay, f of y dot is a function of several variables, and x dx, of course. Okay, so let me call this equation as equation number 1, where y this is expressed as a function of z. Explicitly speaking, you can see that this is a function of y dot only, but implicitly it has got dependence on y and x as well. Okay, because y dot involves okay dy by dx, okay, and so implicitly this function has got dependence on y and x as well. even though the explicit dependence is on y dot as per this equation. Okay, so that is the way. So here you have got j is equal to, so there is a j equal to, now this j only we called as what is known as the functional. J is what is known as the functional. Okay, so you can see why j is known as a functional, because j is depending on a function. So j is a function of a function. Okay, is it not? So j can be regarded as a functional here. Now our task is to find the path between x1 and x2 such that the integral given in equation number 1, which is represented by j, attains a minimum value or extremum value, or any variation in j, that is a language, that is say for j to be an extremum, I am using the general term, for j to be an extremum, any variation in j, any variation in j must be 0. J must vanish. Any variation j must vanish. Okay, whereas you know variation means what? Okay, like in the figure delta y is the variation in y. Okay, similarly the variation in j must vanish. So I can say that is delta, variation is represented by delta j must be 0. Yes, delta j must be what? 0. Okay, or since j is given by equation number 1, I can say that delta of integral from x1 to x2 f of y dot x dx must be equal to 0. Equation number 2. Okay, so now our task is to determine the optimum path which makes j an extremum or stationary. So for this we assume that there exists such a path. Okay, only if you assume that there exists such a path which makes j stationary, we can find it out by just comparing its j, comparing the length of that extremum path with that of any possible neighboring paths. So that is a technique that we are going to do. We first of all assume that there exists an extremum path. For example, we have considered the straight line path in our particular example here, and then compare its length here represented by j. Every such path will be having a definite value of j. Say for the first path the value is j1, another comparison path is having value j2. So you first compare j1 with j2. If you find that j1 is small, then you neglect j2. Then you take another path, comparison path, whose length may be represented by j3. Okay, compare j3 with again j1. Again you found that j1 is lesser, so you neglect what? The second comparison path. Take another comparison path, say whose length is equal to j4. Compare that j4, which is the length, with that of j1. Okay, you once again find that the j1 itself is what? Minimum. So by such repeated comparisons, you will be able to conclude that the path that you have selected mathematically is actually the extremum path, and that is the technique that we are going to do mathematically. Okay, and it is not so hard in the language of mathematics. Okay, and it's got interesting. So for that you have to, so you have got a real path, extremum path, whose length is represented by equation number 1. Now we are going to represent mathematically the comparison paths. Okay, that's what we are going to do in the next step. So to define any comparison path, we have to define some arbitrary deformation of the optimum path. Okay, so we have taken an extremum path. So you have to get from the extremum path, you have to get some comparison path. And you know the comparison path will not be need not be always parallel to the extremum path. So it can have some arbitrary shape. So for example, in this diagram, it is going like this. Okay, there can be something which goes like this. So this is another comparison path. There can be something which can go like this. So there are several comparison paths which is possible. And so since the shape is different, I have to define some arbitrary parameters, okay, by including some new functions and some scale factors. So for that, so let me just go through the next slide. Okay, yeah, right. So in order to define some comparison, to define arbitrary means of any shape, okay, arbitrary comparison paths. So let's introduce, we introduce, this is a mathematical technique, okay, introduce a new function, we are introducing a new function, say eta x, a function of x means the value of eta will be different for different x points, okay, eta x, and a scale factor. Already I have mentioned about the scale factor alpha, to represent the magnitude of variation. So you have already seen that alpha can have different values. When the value of alpha is different, you will be getting different comparison paths, and the shape of the path will be decided by, of course, eta of x, okay, represent the magnitude of the variation, okay, right. So we have defined the new function eta x. So remember that eta x is arbitrary except for one condition. There is one condition. You can select any eta x, but there is one condition or restriction. The restriction is that eta x must be differentiable. Okay, eta x must be a differentiable function. And another restriction is that the value of eta x at the two extremum points, points 1 and 2, that is eta of x1 and eta of x2, okay, the value of this eta x at the extremum point should be equal to 0. That's something very, very important. So whichever arbitrary function which is differentiable and which satisfies equation number 3, what I have written here, can be accepted along with the scale factor alpha to define any arbitrary comparison path which connects the same points 1 and 2. And you can clearly, logically, you can understand why this eta x1 and eta x2 should be equal to 0. Okay, eta x1 and eta x2 should be equal to 0 in order to confirm that, in order to ensure that all the varied or comparison paths is passing through the fixed endpoints. The endpoints are fixed. So when eta x1 and eta x2 is equal to 0, we can ensure that all the comparison paths, whatever comparison paths that we are going to take, all these comparison paths will be just passing through the points 1 and 2. So eta of x1 and eta of x2 is equal to 0. Okay. Now, in terms of this eta x and the scale factor alpha, the path may be represented as. So therefore, the comparison path or the path, okay, any path, in general the comparison path, the path may be represented as, in terms of this okay, eta and alpha, we are representing the comparison path, and the comparison path will reduce to what you call the extremum path for certain cases. Okay, we'll see that the comparison path is represented as y, okay, which is a function of x and alpha. The set of all y, which is a function of all x and alpha, is equal to y, a function of x0. Okay, and you know why, what is it? Please refer to the diagram. This is a point corresponding to any x on the extremum path. Yx0 is a point on the extremum path, the set of all y points. Plus, we are using the two newly introduced quantities, that is alpha, the scale factor, and eta of x, the arbitrary function. which satisfies equation number 3. So this is the equation of the path. And of course, on a close look, you can understand that the moment you put alpha equal to 0 in equation number 4, this gives you the set of all y values corresponding to the extremum path. So when you put alpha equal to 0 here, you know, the second term in equation number 4 will be vanishing, and you'll be getting yx0, the set of all yx0. So you take a different x values, you'll be getting corresponding value of y. So which will be giving you, you can see that it will be giving you a set of points on this one, because alpha is defined equal to 0 for all points on the extremum path. Okay, so you'll be getting the extremum path. So this equation gives you the general equation for any comparison path, which reduces to the extremum path for alpha equal to 0, right? So you can see that yx0 is the where I can just write it here better. Okay, it denotes what? The extremum or optimum. Okay, extremum, another equivalent word is optimum. Extremum path. Okay, extremum path that minimize j, right? And what is that yx alpha? This is actually the representing the comparison path points. Okay, comparison path, is it not? For non-zero alpha not equal to 0. Okay, here it means alpha equal to 0. That's the only thing that, okay, right? Now what we have defined as j in equation number 1. So let's see what was equation number 1. Equation number 1 is j, and we had defined j is equal to integral x1 to x2 f of y dot x dx. But now this y, what I have taken here as y is a function of alpha. Okay, so by equation number 4, y is a function of alpha and j depends on y. So what we can conclude is that j is a function of alpha. Now j is a function of alpha. J is a function of alpha as well. So j has got a dependence on alpha, certainly, is it not? Because when alpha equal to 0, you will get the length of straight line path, which I represent as j1, and when alpha is some non-zero value, you will be getting j2, is it not? So you can see the value of j will now depend upon the value of alpha. For different alpha values, say that this is for alpha, okay, alpha 2 value. Here alpha 1 equal to 0, I can put it like this, and let me say that this is alpha 3 is equal to some non-zero value. Okay, so for that you will be getting j3. So you can see that the value of j will now depend upon the value of alpha. That's why. Okay, that is j is a function of alpha. I'm writing j as a function of alpha now. J, a function of alpha, is equal to, I'm writing it explicitly now. Equation number 1 is now written as x1 to x2 x1 to x2 f of, I'm writing the dependence on alpha as well, f of y, and y already it is a function of x, now it is a function of alpha as well. Okay, yx alpha, then y dot, which is also x and alpha, comma y dot x, that is a function. Okay, equation number 1. Then x, so there is no dependence. X is an independent variable, so there is no dependence on alpha there, so x is independent, quite independent. Okay, so then dx. So we say that this is some equation number, okay, like equation number 5, right? Equation number 5. Moreover, let me make a one more equation from equation number 4, and equation number 4 will give you the variation in y, delta y, that may be useful for us. Delta y, what is delta y? From the diagram we can see this is delta y, right? This is delta y difference. Okay, so delta y is equal to yx alpha, that's the difference between yx alpha and yx0, right? Yx alpha minus yx0, yx alpha minus yx0, which is nothing but equal to what? Alpha times, so that is, okay, only this term will remain, alpha into eta of x. Alpha into eta of x. So let me say that is my equation number 6. Okay. So our aim is to extremize this j, which is now expressed as a function of alpha. And for different value of alpha, you will be getting what? Different value for j, right? Okay, and we are in search of the that path for which this j will be a minimum. Okay, so let's continue. Yes. So now the condition for extrema. Now the condition for extrema. We are for extrema. What is the condition for extrema? We are seeing that the variation in j should be equal to 0. Okay, or in other words, we can put it in the language of differential calculus. The condition for extrema means condition for maximum and minimum. Okay, so we can say it's dou j with respect to dou alpha. Dou j with respect to dou alpha. Dou j with respect to dou alpha, that should be equal to what? 0. This is just like in differential calculus, you have the condition for maxima and minima. First derivative is not like dy by dx should be equal to 0. First derivative must vanish. The same thing we are taking. J is a function of alpha. Remember, j is not only a function of alpha, it is a function of several other variables. Okay, so that is the reason why we are putting the partial derivative here. No other reason. So dou j by dou alpha equal to 0. And you know that will be equal to 0 at which point? At alpha equal to 0. Okay, so dou j by dou alpha equal to 0. Let's say that for alpha equal to 0. Okay, since we have already concluded that the value of alpha for the extremum path is what? 0. So let's find out this condition. Let's use this condition of extremum to find out the relevant equation. Okay, so what we have to do, we have to use equation number 5 as j alpha, and I have to find out dou j by dou alpha. So let me say that this is some equation number 7. Okay, and see that you have equation number 5 with you. So let me take it here from the previous equation. Yeah, that's my equation number 5. Okay, so let me keep it there. Sorry. Okay. Yeah. Just a moment. By the time I take it. Yes, so let's keep it for reference here. So let that be my reference equation, so that, okay, yeah, let that be here. This is for reference. Okay, so I have to take the partial derivative of this j given by equation number 5 with respect to alpha. So that is dou j, simple mathematics only, dou j by dou alpha is equal to, so let me retain the integral sign as such, integral from x1 to x2. Okay, so I have to find out dou j by dou alpha, but you know, f is a function of y, then y is a function of alpha, so I have to use the function of function rule. So what I have to do, so it will be something like, so I use a square bracket here, dou f is a function of y explicitly, so I have to take dou f by dou y, then y is a function of alpha, so I can take dou y by dou alpha, the usual function of function rule, plus same manner second one. What is that? It is dou f by dou y dot, because f is a function of y dot as well, into y dot is a function of alpha, so dou y dot by dou alpha. What will be the next term? So there was a term x. Should I take it dou x by dou y into, what is that? No, you need not take y, because it's sorry, dou f by dou y into dou x by dou alpha, that would be 0 because x is independent. Okay, x is independent of alpha, so only this much is needed. So, and I have to put that integral is with respect to x. So let me say this is some equation number 8 for the time being. Okay, it's a bit lengthy, but you can do it. Okay, so now from some of our previous equation, I have to substitute for two of these quantities. One is I have to substitute for this quantity here, and I have to substitute for this quantity here. That's what I'm going to do. Let me say that this is some quantity A and this is some quantity B. This is what I'm going to do now, okay, from the relevant equation. So you had some equation previously. So let me look at for that equation. Equation number 4. So you had equation number 4 here. See, from that, this is y. You talk of what is dou y by dou alpha. What is dou y by dou alpha? So you are doing partial derivative of of LHS with respect to alpha. So you do it with the RHS. So dou y by dou alpha. So you know the second term only is here is having alpha dependence. The first term alpha equal to 0 already. Okay, so first term will give you 0. So second term you take its derivative with respect to alpha. So that alpha is gone and you are left with only eta of x. Okay, so you'll be getting it as what? Dou y by dou alpha will be equal to simply eta of x. So I am writing it here. Okay, or let me do it. Okay, do it as a side work. So dou y by dou alpha is simply equal to eta of x. Okay, from equation 4. Now one more thing, what I have to, so that is A. Now for B, what we need? I need dou y dot by dou alpha. So what I'm doing, I'm writing is the dou by dou alpha of y dot. What is y dot? Y dot is dy by dx. Okay, so once again I'm writing it is equal to dou by dou alpha of dy by dx. So let's substitute for y from equation number 4 once again. So that is d by dx of what all things? What is y? Y is yx alpha. So yx alpha by equation number 4, it is what? Yx0 plus alpha into eta of x. So I'm breaking it up into two terms. That is again some other brackets I can use. So this is a square bracket now. Yx0 plus what? Alpha into eta of x. Okay, so then of course I have to close it. So that is equal to dou by dou alpha of what you'll be getting? Dou by dou alpha of first thing. So that is dou by dou alpha. You can get rid of all these things. Dou by dou alpha of dy x0 by dx plus what? Alpha is a constant, you know, it's a scale factor, some number. So alpha into d eta x by dx. Okay, you take dou by dou alpha, automatically you know the first term dou by dou alpha will be equal to 0 because it's independent of alpha for alpha equal to 0, and the second function the alpha will be getting rid of and you'll be getting it as simply d eta of x by is not dx. That's what you're going to get. This is by B. So substituting these two things in back to equation number 8. So equation number 8 becomes integral, that is integral again x1 to x2, integral x1 to x2. Just I'm using dou f by dou y, dou f by dou y into a is equal to eta x into eta x. It's quite simple but a bit lengthy, that's all, plus dou f by dou y dot, okay, into the second one is d eta, second time b is has to be improved as d eta x by dx, bracket closed, into dx. Let me say that this is some equation number 9. Okay, now so you what we're going to do is that first term I'll be keeping it as such. So this term I'm keeping it as such, so I'm equal that c, and the second term I'm calling it as d, and I'm going to evaluate d first. I have to do the integration of d first. So d gives what I'm doing integrating by parts, okay. Second term means d, which I have named as second term. Sorry, the second term is integrated by parts. So what will be that one? That is d will give you, what was that? It is integral x1 to x2 dou f by dou y dot into d eta by dx. Okay, that is I'm writing integral x1 to x2, so to be precise, second term, that is dou f by dou y dot into d eta by dx. Okay, into, or okay, it's with respect to x, equal to first term. So how is it? So that is the first term and second term. This is like first function into, so that is dou f by dou y dot into integral of the second function. So integral is with respect to x, so integral of d eta by dx is what? Simply eta of x. So into eta of x, what are the limits? Limits from x1 to x2 minus integral of from x1 to x2 derivative of the first function. What is derivative of the first function? Derivative with respect to x. So I have to write d by dx of first function is dou f by dou y dot into integral of the second, into integral of the second, that is eta of x. Okay, eta of x, and then dx, of course, eta of x dx. That's the thing. Now you just look at the first term in the expansion, first term in the integration by parts expansion. So you know, we had a condition, a restriction on the value of eta x at the points x1 and x2. You know, eta x2 is equal to 0 and eta x1 equal to 0. So this term will make the first term equal to 0. It will be eta x2 minus eta x1, both are 0. So it will be 0 minus 0, 0, 0 into this term is 0. Okay, so what you are left with is only this second term. So you are left with only second term. So now what you have to do, what we are going to do, I'll be writing in the next slide. So what I'm going to do is that I'm substituting for d by this particular term, second term. C is as such. So now looking at C and this equation, so let me say that this is some, this is d, it's, or 10. You can see, can't you see that here there is eta x, here there is eta x. Eta x is common. Integral x1 to x2 is common here. So here also integral x1 to x2 is there with respect to dx. So dx is there. So what you can do, can't you just put it as a single integral with the second term having a negative sign? So what happens here, just if you are going on writing, you will be able to understand better. So what we had here is dou j by dou alpha is equal to integral, the common things I am writing, integral x1 to x2, the first term. What is the first term? That was, I'm writing in a square bracket, dou f by dou y, dou f by dou y. Then the second term, which we obtained through d, was negative, minus d by dx of, minus d by dx of dou f by dou y dot. Okay, and the common term was eta x dx, eta x dx is equal to, okay, is not this dou j by dou alpha should be equal to 0 for extremization. So I can put equal to 0. So that be my continuous equation. I think it is equation number 11. So that's equation number 11. Okay, so dou f by dou y minus d by dx of dou f by dou y dot into eta x is equal to 0. So now you can see that there is no any explicit value of alpha here. Okay, it just saying as such that alpha has been set equal to 0 here in this particular form. Okay, so it's extremization. Now this equation 11 is giving you the condition for extremum path. Okay, now we have seen that the function eta x was chosen as arbitrary function. Okay, so since eta x is arbitrary, it is arbitrary. Since it is arbitrary, it need not be equal to 0 always, right? So how can this integral be always 0? How can equation 11 be always 0? there are two chances. Either the quantity in the bracket which I have underlined should be equal to 0 always, or eta x should be 0 always. But we have taken that eta x is arbitrary. Arbitrary means it can have any value. It need not be 0 always. So the only one and only possibility is that the quantity in the bracket should be always equal to 0. Okay. So equation 11 demands, equation 11 holds good. If and only if. I think you understood the argument here. Okay. For this integral to be equal to 0, for this integral to be 0 always, for the extremum path, either eta x should be equal to 0 always, or the quantity in the bracket should be equal to 0 always. Okay, one of this should happen because it's a product. But eta x we have chosen to be an arbitrary function which need not be always equal to 0 due to its arbitrariness. So the only condition for equation 11 to be satisfied is that the quantity in the bracket should be invariably 0 whenever j is attaining its extremum value. So the condition for extremum turns out to be dou f with respect to dou y minus d by dx of dou f with respect to dou y dot is always equal to 0. Okay, and this equation, okay, this equation is the famous, this equation is the famous Euler's equation. Euler's equation in calculus of variation. Euler's equation. Euler's equation in the calculus of variation. It is the partial differential equation. The relevance of this equation is that it is the partial differential equation that must be satisfied by a function f for the integral of j to be an extremum. Means for the integral of the functional which represents the shortest path here in our specific case to be an extremum or stationary. Therefore we say this is equation 12. For the function f, sorry, for the functional, no, right? For the functional j to be an extremum, for the function, this is our conclusion which we'll be using later, extremum or stationary, for the functional j to be extremum or stationary, the function j is a functional of the function f. The function f must satisfy, this is what you have to take in, okay, take home, satisfy the Euler's equation, given by 12. So for the functional j to be an extremum or stationary, the function f must satisfy the Euler's equation, and that's an interesting thing. If we are able to prove that this function f, whatever be the function, depending on the context, the function f will be different. Sometimes it will be representing the path, sometimes it will be representing some, okay, maybe some time or some other curve, whatever it is. Depending on the problem, it will be different. Okay, so for the functional j to be extremum, the function f must satisfy the Euler's equation, where f is there in j, or j is a function of f. Okay, this is the thing. And why this equation 12 is quite relevant, you'll see that this equation has got a close resemblance with the Lagrange's equation of motion, which is the heart of Lagrangian formulation. If we replace f with L, if you replace f with L, Okay, because we defined f as a function of y, y dot and x. So you can see that it's quite similar to the Lagrangian L, where y is to be understood equivalent to qj. Therefore y dot will be replaced by qj dot, and the independent variable, we have been emphasizing that x is an independent variable. Okay, so x in Lagrangian formulation, you know, time, which is one of the best independent variable. Okay, so if you make such a replacement in equation number 12, you will see that equation number 12 reduces to dou L by dou qj minus d by dt of dou L by dou qj dot is equal to 0. And since it is equal to 0, you can write this equation, this term first and this term second, which is the way in which we have been practicing, right? Okay, Lagrange's equation motion. So due to this reason, this Lagrange's equation motion is also known as the Euler-Lagrange equation of motion. Euler-Lagrange equation of motion. Lagrange's equation of motion is also known in amongst mathematicians as the Euler-Lagrange equation of motion. Okay, because it resembles in general the Euler's equation of motion in calculus of variation. So remember that by this replacement you can reach the Lagrange's equation of motion, whereas the Lagrange's equation of motion can be obtained by several other methods, like starting from D'Alembert's principle. Also you can reach at what? The Lagrange's equation of motion. So we were discussing for the last almost 1 hour, we have been discussing about how to use the calculus of variation technique to arrive at the famous Lagrange's equation of motion. And I hope we will discuss some applications of the calculus of variation, like the Brachistochrone problem, the problem of shortest time of descent, in the next few sessions, so that you understand the relevance of this mathematical technique. Okay, thank you.